Hi, it's Skyler, KD0WHB. In this video, I'll walk you through the construction process and a demonstration of a homebrew AllStar linked amateur radio remote base, headed up to Blue Mountain. A remote base is basically a remote transmitter and receiver that can be operated from anywhere in the world using the internet. In my case, I built a VHF and UHF unit using some old modified commercial radios. Here are all of the parts for the remote base. The heart of the remote base is the GM300 UHF and VHF radio. These radios will be connected to a diplexer and headed out to an external antenna. The GM300s will then have a custom circuit that I built to steer the channel. These will head off to a Raspberry Pi. The radios will also have a USB sound card interface for transmit audio, receive audio, push to talk, and COR. This will also head directly to the Raspberry Pi's USB port. The Raspberry Pi also needs internet, and this will be provided through a MikroTik router. The MikroTik will get internet from a wireless internet service provider up on the same tower on Blue Mountain. In addition, there's also a UHF repeater on the mountain. This repeater also has AllStar link and will connect to another Raspberry Pi to the MikroTik router. The setup is pretty versatile because a station from the internet can talk to the remote base, a station from the repeater can talk to the remote base, a station from the internet can talk to the repeater, and any combination you can think of. Here is the Motorola GM300, the heart of our remote base. This radio is a 16-channel radio but can be modified for up to 40 channels. How do I steer? Well, easily we just simulate up and down presses. Now the way we know what channel we are on is we look at a particular characteristic of a certain channel, and that is number 2. As you notice, the very right bottom segment is unlit. As I steer through every single channel, the very bottom right channel is lit. Now you might ask what happens when I get to channel 12. Well, I've reprogrammed it to something other than 12, so it looks like, same with 22 and 32. So, my program basically scrolls through very quickly until it finds channel 2, and then it pulses the desired amount of times either up or down to get to the desired channel. Here's the control head circuit. This is what I put inside of the radio and what controls channel steering. These are opto-isolators. They just help eliminate interference and false triggering of channel steering. They cut down on RFI a little bit. So when the Raspberry Pi wants the radio to change channels, it just has to send a pulse at its GPIO pin. This transistor amplifies that, goes through an opto-isolator, and then this syncs it and causes the channel up to pulse. Same with channel down. The opposite is true when there is a signal from the radio. When there's a signal there, this transistor amplifies it, makes this LED turn this opto-isolator on, and tells the Raspberry Pi it gets a signal. This is what actually fits right inside of the radio, pops right in, and we wire it directly up to the front panel of the radio, and then we bring a shielded wire out right to the Pi. So here's the UHF GM300 20-channel radio going up to the remote base, and we're going to get this little control head inside of it, or this controller, so we can remotely steer channels. Using some wire, we're going to solder the connections on here to this board, and then going to drill a hole through this to get a shielded cable out to the Raspberry Pi. And the speaker does have to be turned around so we can fit this board right here. Here's the circuit board we will be soldering to. We get all our switches, the 5-volt power, and reading that specific digit from the 7-segment display all off of the back of here. So we'll be soldering wires directly. Okay, here are the guts of the front head wired up, and let's test it to see if it'll work what we just constructed. Have the Pi here hooked up to an Ethernet, and we have our modified control head. If I wrote GPIO pin number 12 and I turn it on, the channels are now steering up. So that's working. It's simulating a button press holding down. Okay, if I do the same for 13, it should do the same type of thing, and yes, the channels are now decreasing. The channel steering seems to be working on this control head we just put together. Now let's package it up, and we will have 2 remote base radios. Both control heads are now wired up and enclosed. On the right here we have the 20-channel UHF remote base radio, and the 40-channel VHF remote base. If I go over to the code and I run my channel steer script on UHF, I can switch the UHF channel, or on VHF, running the 40-channel steer script. For UHF, I'll run the 20-channel steering script I wrote, and so you type that by using /steer20.sh, the channel you want to go to. So let's say I want to go to 5. And then the pins I'm using. So I'm using 12, 13, and 14. So now that's steered to channel 5. For VHF, I'll run steer40.sh. I want to go to channel 16, and pins 0, 2, and 3 are used for the VHF radio. And as you can see, it steers to channel 16. In front of me is the USB sound card interface I built for the remote base. This has 2 sound cards, one for VHF and UHF, and it required modification of the CM108 sound chips by soldering directly to one of the pins. This wire on, the trickiest part of this whole project. So after finding a ham who had just a few extra of these USB radio interfaces by DMK Engineering, I decided to go with this instead of my homebrew fob, because I trust it a little bit more for being on a mountain for years. This is how I interfaced the Raspberry Pi with the outputs and inputs to the radio. Here is the GPIO pins. These are for the channel up and channel down. I have 2 sets, one for the UHF radio, one for the VHF machine. Here is the bash script for the Raspberry Pi that I wrote for channel steering. This script makes use of the wiring Pi library. So you can simply type certain commands from the command line to manipulate and read GPIO pins. At the top you can see the code with a hashtag on front of it, or a pound symbol. That just is a comment, so all this code is ignored just for people to know what the script's actually doing. But the interpreter doesn't actually read it. Bash does not. And at the very top, you can see it says bin bash. That means this is a bash script for the interpreter. Our variables are declared right here. Our node is given for the announcements, the speed which we're exchanging through channels, and a few other variables. So first, we're dealing with the input and output pins. First, here are what the variables are set for. Chan is the actual channel that we want to steer to. Pin up is the argument number 2 on your command line. So when you're typing the command here, let me just give you an example. So when you're typing the command, let me clear it, and so / is how you execute, and then steer. This script is steer40.sh. So now how do I set the channel? I can actually specify that in a command line just by adding a space. So I can say I want to go to channel 16. I want to use pins 0, 2, and 3 on the Pi. So this is equal to $1 on the script. This is equal to the variable $2, $3, and $4. So when I go back into the script, you can see right here, chan equals $1, so channel equals, when I was doing it, /steer.sh 16. So chan as 16. 0, 2, 3 are the pins. Steer 40. So it's not going to execute properly because I don't have the radio plugged in. But this is $1, this is $2, and this is $3 in the script. So these are set variables that can be accessed just by manipulating the way you run the script. These are the modes of the GPIO pins. These both are inputs. No, this is an input. We're using an internal pull-up resistor, and then these both are outputs. So $up, which is equal to the command line argument number 2, $2. Okay, we disable the transmitter for the duration of the script. And the reason we do this is because I do not want the actual remote base to play the audio files, and because we're writing a playback command, so all nodes hear it, the remote base will actually transmit it out of its transmitter. So that's what this command is. It disables transmit, and now we're going to just set the GPIO bins to 0 just in case they are something else. Here we are actually reading the input segment. So the variable seg equals, we read it, and then now we're gonna play please wait a moment while it's steering. Okay, here is the first active part of the script. It's the while loop. This part of the script simply pulses, and it keeps pulsing through all the channels until it realizes that it's at channel 2. And how do we know that? Well, it's that one segment at the very bottom right that is off for channel 2. Okay, so we have a while loop while the channel segment is not equal to the value 0. So if it's a 1, it's always 1, it's always on unless it's on channel 2. So we have this loop that runs until it meets the condition, and then it's at channel 2. We have it write the GPIO pin, and we have it sleep for the certain amount of time we specify, and then we have it write it, and then we have it write it to 0. So this simulates a pulse. These 4 lines of code simulate a pulse, and then I just have this echo. It echoes back in command line for debug. It's not important for a remote base. So now we keep reading it. At the very end of the while loop, we keep reading it to keep checking. So that's what this line does. And a done specifies the end of the while loop. Again, this is for debugging. It echoes that we passed this while loop. We will not pass the while loop if the radio is off, because it will always think it'll just keep trying, and it won't get any signal back. So we won't pass this loop unless the radio is actually turned on and all the wires are hooked up right. Okay, so now that we know that we're on channel 2, it is time to predict how we get to the channel we go to. So let's say we're on this one, in our particular case, we're on a 40
channel radio. So if we're on 2 and we need to get to 30, it's obviously quicker to go using down arrows and pulse down. So if it equals 2, there's nothing more required because it's already there. If the desired channel, that's $sign channel is the desired channel. So if it equals 2, we don't have to do anything. And for some reason I had to add some code, so I just did a dummy variable z equals 1. You have to have some code, I guess, in this if statement for it to actually do something. Or actually, yeah. Else if channel equals 1, so if we're on channel 1, I didn't want to write a specific thing for that. We gotta just pulse it down once, so we write it to 1 and then to 0. That simulates a pulse. If channel is greater than 22 or less than 40, in this case, it's quicker to use down arrows. So we set this place mark. This calculation right here actually tells us the amount of pulses we have to down pulses we have to do to get to the desired channel. So if it's greater than 22 or less than or equal to 40, we know that we have to go down. So now this just tells us how many pulses down. So now this for loop actually will pulse it that amount of times, the down arrow on the channel. That's what this for loop here does. And then now we also have the condition where it's quicker to go up. If the channel is less than or equal to 20 or greater than 2, it's quicker to use up arrows to get to the desired channel. So in this case, we simply just have to have the place mark as the channel variable, the desired channel minus 2. Since we're on 2 and we want to get to desired, let's say 4, we simply just have to do 4 minus 2, and that means we have to do 2 pulses to get from channel 2 to 4. Or if it's 6, since we're on 2, we know we're on channel 2, we have to do 6 minus 2, so we have to get 4 pulses to get to 6. So that's what this place mark does. And again, we have another for loop which will pulse the correct amount of times from 1 to place mark, and that'll pulse. So now that we're done, we have some code. This is simply for the channel playback, so we get an announcement on what channel we steered to. Here I just have different cases. If the channel is less than or equal to 20, we have all digits 1 through 19 already made, so all we have to do is combine, and we're using the cat command to combine raw audio files in the .ulaw format. So we'll just combine var_lib sounds channel and then the desired channel. So if we're on channel 16, we'll combine channel 16 and then we'll do a playback over the radio. So it'll do RPT playback and then this temporary file will be created. And it'll at another debug, it'll say we successfully steered and the channel is 20 below. In different cases, we have to combine more stuff. If it's like 21 through 29, we have to combine 20 and the other digit, channel minus 20. So if it's 21, we have combined 20, and then 21 minus 20 equals 1. So it would say 21, and it'll play that back. And we have that from 30 to 40, and that's basically it. The end of our if statement here, and then I'm actually going to remove this. I think I'm going to have the user required to manually re-enable the transmitter with the access code. But anyway, this re-enables the transmitter when this script is finished. So that's basically the entirety of the channel steering script. And now we execute this script from the rpt.conf file. So nano etc asterisk rpt.conf. And in this file, we actually can specify the DTMF functions to execute the script. I don't have this finished, but you can see these 3 are finished. We have the command 9701 on DTMF, and it will execute the script etc asterisk script steer40.sh, and then we want to go to channel 1 using GPIO pin 0, 2, 3. So haven't finished this yet, but that will be what this does. That's weird. I don't know what this is doing here. Oh, I know what happened. Yeah. So anyway, that's basically it for channel steering. There's other configuration, but for channel steering, I think I covered it. Here's the router that we'll deploy up on the mountain. It'll take the wireless internet service provider and give us internet to the Raspberry Pi, both the remote base and the AllStar linked repeater. It's a MikroTik Linux router, and for about $100, this router does everything a $2,000 router can do. It's Linux, so it's a little harder to use, but the programs like Winbox make it pretty easy.
To configure the MikroTik, all you have to do is plug in an Ethernet cable from your computer to one of the LAN ports on your router. The easiest way to configure settings and log into the router is through a program called Winbox, available for Mac and PC. When you're in the MikroTik software, it will prompt you with a login. In my case, the IP of the MikroTik is 192.168.88.1. The login is admin, and the password by default is blank. So, when I click connect, it'll log in, and now I'm on the menu for the router. All I needed to do was basically set a DHCP reservation for each Raspberry Pi and forward ports to it for AllStar link and remote login. So, to set a DHCP reservation, I went to IP, DHCP server, and now you can see repeater Pi, the reservation on its local address, and then the MAC address of it, and then the remote base Raspberry Pi. So we have two Pis. That's my Mac, but that doesn't matter. That won't be plugged in up there. So we have two reservations on 88.5 and 88.4 IP addresses for these devices. The only other thing I had to do really was go to IP and then hit firewall, and then in AT I had to add DST NAT rules. And this isn't what it's going to be, but right now I have port 22 open up to the IP 192.168.88.4. That is all I had to do on the router. You can do a lot more, though, for different needs. It's time for the moment of truth. I have the VHF unit hooked up to the Raspberry Pi with the DMK Engineering USB radio interface. I'm not doing UHF right now because it basically works the same. I have a Kenwood 440 mobile, 2-meter 440 mobile, hooked into an antenna outside, going directly to Jerry W0GV's repeater, and a power supply here. So with this Kenwood mobile, I'm going to call out to my node here, and I should be connecting right in. KD0WHB 442622.
Node 42622 connected to node 42845.
Okay, now we are connected to 42622, my node. So now if I dial remote command mode, I should be able to remotely control the transmitter.
Remote control mode.
And now let's see if I can steer to channel 1, which is 5.2 simplex. I have my handheld here. So we'll see if we can hear ourselves on it. KD0WHB steering channel.
Remote VHF transmitter disabled.
Awesome.
Channel 1.
And now we are steered to channel 1. If I call my handheld on 5.2 simplex, we should now hear it on the speaker out here. Kilowatt Delta 0 Whiskey Hotel Bravo. Testing. Awesome, so the remote base is working and the channel steer function is good. This demo demonstrates both remote base radios operating as a crossband repeater. For proof of concept only, because this is not a crossband repeater. Okay, so we've got, let me get this out of the way, that's not part of this. We've got the two radios stacked. VHF is on the bottom, UHF is on the top. Now, these are both into a dummy load, and I also have these two radios, which are both on extremely low power, so it's not going to get out too far. I have the top one on 446.0 simplex, and then the bottom on 146.5.2. So currently, if I key up on this bottom radio, I should come out on the top. So I'm going to key up, I'm going to talk on 5.2, and you should hear me on 446. KD0, WHB, testing 1, 2, 3, 3, 2, 1. Okay, now if I come in on 446, I'll come out on 5.2. Kilo Delta Zero, Whiskey Hotel Bravo, testing. And you can hear the echo, but it's definitely working, so these both work. If I, right now since they're connected together, if a remote station keys, they'll both key up, but these are remote bases. It's not a crossband repeater, so we're not going to need them both connected together.